Okay, so what you see on the screen is this is just our summary of what we've done last week and up through even today. I'll post this picture up. You can download it if you haven't already gotten a copy of it, written it down or something like that. So make sure that you go and spend a little bit of time reviewing this. If there's things here that you don't know how to use, well, that's something you want to ask about. I went ahead and for the unit conversions, this stuff right in here, I went ahead and I just kind of wrote down all the different things that we had talked about. Some people were talking about miles. I can't remember how many feet in a mile. There you go. Okay. Now it's all on you. You got it. You got it written down. It's all condensed together. Make sure you know how to use those things. All right. Let me go back. Here we go. In this particular example, I ask you to, well, this is a really great problem for several reasons. Number one, it's nothing complicated. The math involved here is just the basic math that we've been doing with the different formulas. The hard part about this problem in particular is putting the pieces together and figuring out what it is that you need. Because a lot of times you can't, if I don't know what I'm trying to find, then I don't know where to go with this. I've got the numbers, I've got them down, but what am I trying to find? And this one was really interesting that it doesn't really specify what you have to do to get the answer. You kind of have to know that. You kind of have to know where you're going with it. And so the problem states that you have a saw blade. The saw blade is 10 inches in diameter. Okay, so the whole thing would be 10 inches across. So I'll put 5 inches for the diameter because that's the number we're going to need. For the radius. It also tells me that it has a, there we go, every time. Okay, 2,000 is my revolutions per second, or per minute. So it's going to spin. It spins 2,000 times in 1 minute. It also tells me that there are 12 teeth for every inch around the outside of that saw blade. Okay, so really, really small teeth to cut whatever you're going to be cutting. So you can see the picture here. There'd be 12 teeth all the way around that. So what we want to be able to do is we want to figure out in 1 second, how many teeth, how many individual teeth are going to be passing through whatever it is you're cutting. So if we time for 1 second, how many times it spins around and how many teeth would actually cut into your object. So what do we need to do? What?
Find out how many times it spins.
That's really good. The first question I need to think about. Well, the question says, how many times in 1 second? How many teeth cut through in 1 second? So the first thing I thought of was, well, how many times does that thing spin around in 1 second? I didn't tell you per seconds. How many times did it spin around in per minutes? So it's a problem. I need to convert my rate. This is my angular speed. They gave it to me in revolutions per minute. So it spins around 2,000 times in 1 minute. Well, how many times does it spin around in a second? We can convert revolutions per minute to revolutions per second by simply converting the minutes into seconds. So we get, works out right here. Okay, that's off. 2,000 divided by 60 equals 33.33 revolutions per second. Okay, now 33.33 feet, revolutions per second. In one time, that thing spins around. In 1 second, it spins around in 33 times, basically. A little bit more than 33 times. So what's the next question that you need to ask? How many teeth are on the blade itself? If I know how many, if that blade just spun around 1 time, then every single tooth would have passed through that piece of wood or whatever you're cutting. Well, how many teeth are on my saw blade?
If it, you have to figure out what's per inch and then multiply it.
Good. Right? So, what's that word? Circumference. How far is it around the whole circle?
360 degrees.
Nope. Okay. What? do you notice what that formula is? Isn't that the same thing as, that's S equals R theta, right? That's arc length. But how far is it around the whole circle? 2 pi times R theta. So circumference is really a way of finding arc length. But circumference just represents one kind of arc length, the whole thing. If I were to measure inches around that circle, I would be able to tell you how many teeth are in that saw blade, because we know that for every single inch, right, for every single inch there's 12 teeth, right? They told us in the problem 12 teeth for every inch. So if I can tell you the inches, the circumference, I can multiply by 12 and I can get the approximate number of teeth around that saw blade. So here, I go ahead, we got our formula here. We're going to plug in the radius from our circle, or from our saw blade. 2 times 5 times pi is 10 pi. If I'd asked you what the circumference was, 10 pi is a perfectly acceptable answer. I prefer the pi rather than the decimal. Titus? Okay? But I went ahead and wrote it out for you. There's the decimal approximation. It's 31.4 inches around from the beginning all the way back to the beginning of that saw blade. So if you have 31.4 inches, how many teeth does it have? Okay, well 31.4 times 12, 370, approximately 77 teeth. That saw blade is not the actual saw blade. It's just a representation. The saw blade we actually are using has much smaller teeth, doesn't it? In 1 inch, you only have maybe 2 teeth, 3 teeth on this blade. Okay? So if I know that there's approximately 377 teeth, and it's going to spin around 33 times, 33.33 times, how many, you tell me, how would we do that? It's going to spin around, so for every 1 revolution, 376.8 teeth, approximately, are going to touch that thing. Let's do it at 33.33 times. You tell me the number of teeth. Find it out real fast. I mean, find the number of, how many teeth actually get into that.
So like per second?
For every second, this is pretty impressive. For every second this saw blade is on, okay, it's cutting into some object, 12,565.41 teeth are cutting into whatever object it is. Hopefully it won't be your finger. You won't even know before it cut it off. Unless you have a fancy saw in it. Some of the saws nowadays are moisture sensitive.
Oh, yeah.
It shuts off before it, like it gets 1 drop of blood on it, boom, it locks out. It actually destroys some of the mechanisms. So it stops it almost instantly. Okay? Questions on this part? How do we get where?
It's 12.
The question was, let's go back and talk about circumference for a second. Right? Circumference, I'm actually using that formula where it says S equals R theta. The arc length, so in physical actual distance, in this case inches, if I were to take a tape measure and wrap around the whole circle, how far would it be? How far would the tape measure wrap around, right? And so the radius of that circle is 5. Well, how far did you wrap it around? Well, we went all the way around the circle. Remember, this formula needs to have radians involved. So we had to put it in terms of 2 pi, that's theta, so 2 pi here is theta, and r equals 5. So we took these two values, we plugged them in to our formula, and worked them out. So 2 times 5 would be 10 pi, or 31.4. I think they went 31.415 to be exact.
How'd you get 5 for R?
they told me the diameter was 10, right? And so if the diameter is 10, the radius would be 5. That part has, I have to know that or I can't do the problem.
Like where they don't tell you.
We're going to do another problem, but not like this. But here again, it's a good exercise. Okay, the next problem. This is number 55. Shh. 55, this one's a bit tricky too, but it's not as in-depth as the one before. Will be. Okay. You have 2 wheels. You've got a larger wheel with 7 centimeters, and you have a small wheel that has a radius of 4 centimeters. There's a belt that goes around both wheels. And this is a part of an air conditioning unit. Okay? It's part of the mechanism that turns the fans. And so, as the belt travels around both wheels, they spin, and that's how the mechanism works. What they've told me, other than the radii, they've told me that the large wheel spins at 120 revolutions per minute. So for 1 minute, I could count how much time that would go around itself 120 times. Okay? Some of the formulas that are really relevant and really important for us to note are listed on the board. W is what? It's actually not W, but omega. Okay? That's angular speed. What's V? That's linear velocity. Something that I wrote down earlier was this one. I didn't specify that specifically, but that's the key to this problem. That linear velocity is just angular velocity times the radius. That's the connection. If I have angular velocity, I simply multiply by the radius to get linear. If I have linear velocity, I divide by the radius to get the angular velocity. That's really key to understanding this problem. Right? And since there's theta over time and theta over time, we can substitute out the W for the theta over time. Right? See, when you see these two pieces right here, they're the same things. That's how you get this formula. So the bottom part got cut off because of the way that the document transferred over. Let's fill in what's missing. I was asked in part A to convert from revolutions per minute to radians per second. So I got to convert minutes into seconds. That's an easy one. And I have to convert revolutions to radians. Same thing. This is day 3 of doing this kind of stuff. So you should have a pretty good grasp on this one. So to convert the minutes, right? So this would be minutes on the bottom. What about for the next one? What are we going to put on the bottom for that one? Okay, 60 seconds. No, it can be anything. Yeah. All right, so the minutes get canceled out. Now, if I were to complete this problem right now, I would have revolutions per second. Minutes are on the bottom. They gave it to me. This is what they gave me. Right? We need this to start with. Allow the units they give you to dictate how you put up the unit conversions. I need to get rid of the revolutions, so we got to put a revolution in the bottom, right? So it's going to be something. Revolutions. 2 pi is how many revolutions? 1. Just 1.
What is? Oh, that's REV.
Yep. So the revolutions cancel here, and they cancel there. So I'm left with radians on top and seconds on the bottom. When you multiply this all together, it ends up giving you 4 pi radians per second. If you multiply through and you got 12 point something for your decimal, that's okay too. I prefer to leave it as just the whole value for pi. Part A, easy enough. That's just traditional unit conversion. No special requirements to do anything there. Same thing for B, actually. Let's look at B. Okay. So B says, okay, now you've got the angular speed in radians per second. I want you to tell me what is the linear speed of the belt that travels around both wheels? Do you think, let's just pause a minute. Do you think the belt's going to be traveling around both wheels at the same speed because they're different sizes? Or does the belt travel faster around one wheel and slower around the other wheel? Well, imagine this. Imagine you're driving a car that has two different size tires. The front tires are small, the back tires are large. If you're driving down the road at 55 miles an hour, do you think they're turning, the linear speed is different? Because that would mean the front of your car is going faster than the back of your car. Eventually you're going to rip in half. Okay? No, that's not true. It means that one tire spins differently. The angular speed is different. The linear speed would have to be the same for both. Because that belt that's traveling around, that belt's traveling the same speed around both wheels. The wheels spin. The smaller wheel has to spin faster to keep up with the big wheel, right? So the angular speed is different, but the linear speed is the same. Okay? So the next question says, what's the linear speed of the big wheel? Shh. I told you earlier, linear speed is just the angular speed times the radius. So, I love that thing right there. It's really great. Multiply these two together. So we have, this part comes from the previous example. That was the answer to the previous problem. A, 4 pi, that's the angular speed. The radius of my big circle, 7. So 7 times 4. So that belt travels around at 28 pi centimeters per second. That's my linear speed of my belt. The last question is the one that gives most people the issue. If you're looking at the last problem, right? So when you come over here and you look at it, you've got a couple of things to look at. Why did we set it up like this? 28 pi equals 4 omega. Where does all that come from?
4 is the other.
So remember, I'm asking you for angular speed of the smaller wheel. That's what C asks for. So in generic terms, we have V equals R times omega. I want omega. That's what I don't know. But I do know the radius is 4. And I know, here's the part that you had to recognize, that 28 pi is the linear speed of the small wheel too. Because that belt travels around both wheels in the same speed. So when you plug that in, you just solve for omega, and you're done. So 4's cancel out. 28 divided by 4, 7 pi radians per second. What's that? Omega is angular speed. Write it down. I think about it, the omega is kind of very curved, so it's kind of looping. So you've got, it's going around in circles. Okay? Questions about that problem? We good? Both really, really good problems. You need to check it out. Go back, watch the video, download the document, or go back and look at your notes. Let's start next stuff. All right, so I have to change. This is not 1. That should be a 2. Don't you love that thing? Trigonometric functions. Here we're going to be talking about sine, cosine, tangent, cosecant, secant, and cotangent. Today's lesson is actually really easy. Okay? For a number of reasons. Number 1, majority of you have already seen this. Number 2, there's really not a lot to do with it. But the downside is if you don't learn it, it's going to be rough. I want you to take a second, and I want to see if you can remember. We did this yesterday for a little bit. I want you to take that triangle, and I want you to take, I've already labeled the angle I want you to look at. So here's theta. I want you to make all 6 trig functions over here, right? And I want you to tell me, if I use theta, what are the 6 trig functions? Go. Let's go and write them up. Okay? Sine of theta is what? Okay, it's the opposite over the hypotenuse. What about cosine? The adjacent over the hypotenuse. And tangent? Opposite over the hypotenuse. Oscar had a heap of apples. Yep, it should be A. Okay, so, ka, toa. Okay, there's a whole bunch of ways you can memorize it. If you don't have it memorized yet, that's in your best interest to memorize or just learn it however you want to. Here's the easy part. I'm not asking you to memorize the next piece, right? When we're looking at cosecant, secant, and cotangent, these three over here, it's based on what I did on this side. Don't say the word inverse. Keep that out of your mouth for now. Because they are not technically what we want to call an inverse. But they are reciprocals of each other. The word reciprocal means take the fraction and do what with it? Flip it over. So cosecant would be what?
H over O.
H over O. Secant.
H over A.
And then cotangent. Okay. That is 4.2. If you get that, you've got a huge portion of what we're doing. Okay? That's a good thing. Let's do an example. I want you to find all 6 trig functions for that triangle. Let's call it, let's say that this is angle A. What do you know? All right? So at that point, find the trig functions for this, for the angle at the bottom down there where A is, right here. All right, let's write them. Sine of A is what? Don't rationalize. Just tell me straightforward.
1 over square root of 2.
Okay? What's the cosine of A?
Same thing.
1 over the square root of 2. What's the tangent?
1.
It's 1. Cosecant?
Square root of 2.
That's easy. We go back and we can look over here at this side and we can tell you, well, if that's that way, I'm just going to flip this thing over to get whatever's at cosecant. So we have the square root of 2 over 1, and then secant of A is going to be equal to the square root of 2, and then cotangent of A is going to be also equal to 1. This, what we just did, is big deal. It's going to come up over and over and over. You're going to see these results a lot of the time. They may be rationalized. What is this the same as in terms of rationalization?
2. Square root of 2 over 2.
So know that that and that are the same thing. Okay, that will come up from time to time. Yep.
What about, can you go back?
Okay.
What about like, how do you know which one is O and A on the sides of the triangle?
Okay. If we start out at A, totally. If I'm looking at this angle down here, what side length is opposite that angle? This one is the opposite. That one is adjacent to it, right?
Oh, okay. I see.
It's positional values. If I change to the other angle, then now the other side is now opposite. That's relative to you. You have to master that idea because we're going to change triangles all the time. And the opposite won't always be in the same place. So be careful. Square root of 2 over 2. That's really wonderful. Square root of 2 over 2, rationalize. What's the square root of 4? 2. There you go. Okay, let's see if I can do this. Yeah, there we go. Is that all of it? Yeah. All right, let's go on to the next page. Okay, so here again, we're looking at trig functions. Do this for 30, 60, 90, but let's go ahead and let's pick this one. Oh. I want you to find all 6 trig functions for angle A. All right, here we go. Sine of 30 is equal to the opposite over the hypotenuse, 1/2. The cosine of 30 is equal to the adjacent over the hypotenuse. That's going to be square root of 3 over 2. And then tangent of 30 is the opposite over the adjacent. That would be 1 over the square root of 3. To get cosecant, we just flip those around. So that would be 2. We're going to flip over cosine for secant of 30. That's going to be 2 over the square root of 3. And then cotangent of 30 would be equal to the square root of 3. Any questions? Okay. I'll let you write that down. We got one more thing. Watch. Okay. Look at the bottom for me here.
You need to do it so well.
Okay. This is a little preview. Listen to me carefully. Do you all agree with me that that's 0 degrees? That's 90 degrees. If I went up like that, if I go all the way around, what is it? Well, all around here, that would be 270. All the way around would be 360. We good on that?
Yeah.
Something to note that's really useful for the unit circle, not to mention the quiz. That if you go on the unit circle, like pulling out your unit circle sheet and look at those coordinates, the cosine of that angle is always the x-coordinate. The sine of that angle is always its y-coordinates. So, what's the sine of 90 degrees? It's 1. What's the cosine of 180? -1. What's the tangent of 270? Uh-oh. What's tangent? It's the y divided by the x. So the y divided by the x. -1 over 0, which means it is undefined. It isn't a real number. Wink, wink. Okay? When your trig function is over something over 0, it means there's no real value there. It doesn't exist. If you really want to go into this, put your unit circle out. We just found the sine, the cosine, and the tangent for 45 and for 30. Look at the coordinates for 30 degrees and the coordinates for 45. And you'll see the same answers that you found today by using the triangle.
Look at that.